Hello everyone, my name is Ertan Umit. I'm from QARMAN Institute. Sorry for the jet lag infused presentation. And this is the QBSat we are developing currently. Its name is Karman, and we are hoping to establish a safe reentry after some orbit time. So. In general, our motivation is to demonstrate the feasibility of a CubeSat in the reentry. We are not reinventing the wheel, as my colleague said. We are just trying to fit something smaller and cheaper for reentry measurements and operations. I'm going to talk about a little bit about our challenges. Here we have our some of our missions. For example, the thermal and the structural design is very crucial for us. And we have the payloads, the scientific investigations, the XPL. As you see here, we have a communication system, and we also have an orbital mission that is different than the reentry part. Here you go. Here you see the 5 phase of the mission. Right after the injection, we have the commissioning phase and the detumbling phase. After that, we have the first phase that is developed by the University of Liège in Belgium. What they are doing is actually, by changing the attitude of the satellite, they are trying to do simple orbital maneuvers using the different drag on that atmosphere. And that phase will be about 1 month. After that phase, we will going to deploy our panels, as you see here. So the first month, the panels will be on stowed configuration, and after that, depending on the launch altitude, depending again, we are a QB50 mission. Maybe I'm sure most of you are aware of the QB50 project. So since the launcher is not being fixed yet, we are going to have 3 to 4 months of deorbiting time, and after that we will have as we call ourselves, 20 minutes of hell, this reentry process, and after that we will have 4 minutes of data communication time, and then we are basically crash landing somewhere on Earth. And here's our 4 main challenges. First, we have to fit everything on a 3U CubeSat, all the payloads, everything, and we have the weight limitations, etc. Then we have the thermal protection challenge that has to survive up to 5,000 degrees during reentry on the stagnation point. Then we have the challenge of communication. We have a really short window for communication, and we don't know where we are landing. So that's why we are planning to use the Iridium network. And then we have the stability concerns. As you see from the pictures, we don't look like the normal reentry capsules. Our shape is really different than the, let's say, normal missions. So here's the design of our satellite. As you see, our nose, our structure is not like a normal CubeSat, 3U CubeSat. We have a cork nose. That's the TPS system that has to survive the 20 minutes of hell. And we have several payloads in the cork. And on the back side, we have all the avionics systems. And on the rear part, we have the antennas. That's the engineering model, or the mock-up model. I'd like to call it better. Up to here, we have the reentry payloads inside the cork, and the remaining parts are normal CubeSat components, like the EPS and ADCS. And on the back, we also have some sensor payloads. That's the backside of the satellite, and that is the only interface we have because of the high thermal loads. We have to protect all the satellite, all the outside, and we only have contacts from the backside. That is the front side. You see some payloads, entrance points on the cork. That's the electrical design. I'm going a bit fast on this. If you have questions, I can go more detail. That's one of the main payloads for the reentry. IRSDS. We have the aerodynamic stability control mechanism. You see here the panels. We have one PhD that is working to design this aerodynamic stability for the reentry. All the panels are manufactured by silicon carbide for the temperatures, and the solar panels will only be during the orbital time. During the reentry, they will melt, and we will survive with the batteries. This is the second and the major payload of Karman. Most of them are located in the cork, and we are measuring the pressures. We have 7 pressure sensors and 40 temperature sensors all around the satellite to validate the reentry models and the TPS system. We also have a spectrometer on the stagnation point to measure the plasma sheet in front of the satellite. That is the payload design in the cork. These are the payloads on the sides, the pressure sensors, pressure inputs. That's the spectrometer. This is the TPS. So normally all the reentry missions, or majority of the reentry missions, you have one capsule that has to survive only the reentry part. But since we have at least 4 months of orbital period, we cannot fill the satellite with insulation, because then we'll start melting on the inside during the orbital time. So we decided to separate the satellite in 2 parts. The first part is the orbital operational part that are not protected with the insulative material. These are outside of what we call the survival unit. The survival unit is this part, and that part here is insulated with the aerogel material. This is the highest insulative material for now, and that is the only thing that can survive with the 1 centimeter of insulation. And during the orbital period, all the components outside of the survival unit, they will be operational, and then during the reentry, they will simply melt down, and the ones in the survival unit, they will hopefully survive. These are some pictures of the tests we done in the plasmatron facility in von Karman Institute. These are more detailed images of the survival unit. We have the Iridium modem and the batteries here. And the second major issue we have for the reentry is the communication. Again, since we don't know where we're landing, we have to have some sort of global coverage. And currently Iridium network is the only thing that can provide global coverage 24/7. Although it has a really low communication rate, we had to survive with that. And we cannot also use that during the reentry because of the blackout, because of the low frequency of the Iridium. That's why we had to come up with a data compression and the data prioritization mechanism to get as much as data as possible. As a conclusion, again, we are facing 4 main challenges, and we kind of solved 3 of them, except for the Iridium, which is also a major issue for the big guys from NASA and ESA. They also have faced some issues on this. We are hoping to test it detailedly in the future. Actually, we are going to test the RF mechanism next week at Aztec, and all the scientific objectives, etc., they are tested and validated on ground. We are waiting for the launch of the QB50 now. So this project is supported by the ESA GSTP, and if you have any questions, contact me on this address.
Do you plan to have some controlled reentry? That means you have some guidance control system to control the position of the landing?
No.
No?
No, we are absolutely unsure where we are landing.
So isn't it dangerous?
It is, and that was actually the first requirement by ESA, because they have high restrictions about deorbiting. But the simulations show that we are 3 orders of magnitude safer than the legal limits of actually hurting anything. So we are assuming we are safe.
Okay. Why it is not so dangerous? So because it's too small or too light?
Yes, actually it all depends on your kinetic energy. So since we are really low and most of the satellite will actually melt, our mass will be decreased, and the velocity also will be really decreased because of the panels. So the kinetic energy will be really low. I don't remember the real numbers, but it was lower than seriously 10,000 times less than the legal limits.
I have an engineering process question. So what you're testing is really the temperature, vibration, and shock, and other things. So is that something that you can test in the laboratory before you go up there?
Some of them, yes. Some of them, no.
And do you do that?
Yes, actually in QARMAN we have too many facilities to test a lot of things. First of all, the plasmatron facility actually was one of the reasons we are developing this, because they have in-house developed models for this, plasma models, ablation models, etc. And we have been doing quite extensively testing all these models with the TPS we have. For the IRSDS part, however, it's a bit more difficult because the Mach number is really high, and to test this, we are actually doing a test mechanism for this, but it's not been done so far.
Okay, so you consider this as the final in situ experiment, so to speak.
Exactly.
Okay,
Yeah.
thank you very much.
Now there are many CubeSats in very low Earth orbit that come back into the atmosphere in a short time. So have you considered how to make your ablation device modular to possibly attach to one of the many CubeSats that are reentering?
No, but we are actually hoping to keep all the structure and the survival unit part, so that we can continue testing or using this structure, all the mission for the future missions, so that people also can conveniently test their systems for the reentry part.
Okay, so you could make this available to as a secondary payload on other missions?